Now we are moving on to question number 2, 2018, February, March 22. This question is about different types of compounds, or elements rather. Question focuses on carbon and silicon. They are both in group 14. Group 14 means group 4 actually. C60 and diamond are allotropes of carbon. They use the lattice structure of solid carbon 60. Now, because this question is about allotropes of carbon, I want to talk about what allotropes are. And then there are allotropes of carbon. I will first have a discussion on them. What are allotropes first? Allotropes are substances of the same element. Allotropes are substances of the same element having different bond arrangements, to give different physical properties. They have different physical properties. Now, I can talk about examples for allotropes of carbon. Allotropes of carbon. Allotropes of carbons fall in 4 areas in 3 categories. The first one is diamond. And then we have graphite. Diamond, graphite. And we go to the next one, they are called fullerenes. Under fullerenes, there are 2 substances. First one is Buckminster fullerenes. Buckminster fullerenes. And the other one is nanotubes. Buckminster fullerenes are also commonly known as buckyballs. So I'll write that also. I'll take it. If you go to diamond, first I'll start with hybridization. They are all made up of carbon. Here we can see carbon shows diamond has each carbon with 4 other atoms bonded to. So it shows sp3 hybridization. sp3 hybridization. In graphite, we have 1 carbon connected to 3 other carbon atoms. In such a situation, here also carbon shows this is not sp3, it is sp2. sp2. Graphite has carbon atoms bonded to 3 other carbon atoms. They show sp2 hybridization. And in Buckminster fullerenes, sp2 hybridization. And then in nanotubes, again, carbon shows sp2 hybridization. Here I can write about the number of carbon atoms. Each carbon bonded to 4 carbon atoms. But in graphite, each carbon is bonded to 3 carbon. In buckyballs, each carbon is bonded to 3 carbon atoms. In nanotubes also, each carbon is bonded to 3 carbon atoms. We'll go to the next part. Here, we'll talk about this type of particle arrangement here. In diamond, we can see diamond a giant covalent lattice. A giant diamond is a giant covalent lattice. Even graphite, a giant covalent lattice. Giant covalent lattice. Buckminster-Furan, I can say, a molecular lattice. Simple molecular lattice. It is made up of molecules. But nanotubes are again giant covalent lattice. Giant covalent lattice. Only one molecular lattice is there, it is buckyballs. And for graphite, I can write one more thing, even though it's a giant covalent lattice, it's a layered structure. Now we'll talk about electricity conductivity. Diamond and insulator. Diamond is an insulator. Graphite is a conductor. Conductor. Buckminster-Furan, buckyballs, insulator. Nanotubes, they can conduct. I can say conductor. And then type of bonds available. Contains covalent bonds. Diamonds contain covalent bonds. Graphite contains covalent bonds. Covalent N contains covalent N van der Waals forces. van der Waals forces. Contains covalent and I'll write covalent bonds and van der Waals forces. And in buckyballs also we have covalent bonds and van der Waals forces. But in nanotubes we have covalent bonds. If you talk about melting points and boiling points, diamond has, I talk about high melting point. You don't have to talk about boiling point when you talk about high melting point. So high melting point is for diamond. For graphite also, high melting point. But for Buckminster fullerenes, we have relatively low melting point. And nanotubes have high melting point. This is a comparison of the allotropes of carbon. If you want, you can copy this down, or else you can take a screenshot also. I think taking a screenshot is better, saves time. So this is a final table of comparison of properties of diamond, graphite, and fullerenes, which are of course of allotropes of carbon. Now with this knowledge, we can go to the question. Carbon and silicon are elements in group 14. Carbon 60 and diamond are allotropes of carbon. Describe the lattice structure of solid C60. C60, it comes under Buckminster fullerenes, and it's a molecular lattice. It's a molecular lattice. So we have discussed the molecular lattice of C60. 2 marks are there. I can write first about particles of C60. We can say C60 C60 molecules contain strong covalent bonds. C60 molecules contain strong covalent bonds. These molecules are attracted and held together through weak van der Waals forces. Weak van der Waals forces. C60 molecules contain strong covalent bonds. These molecules are attracted. These molecules are attracted and held together. We can say these molecules are attracted weakly. It's better. Weakly and held together through weak van der Waals forces. Yeah, that's enough. For writing C60 molecules made up of covalent bonds, you get 1 mark. And these molecules are attracted together and they are close together, but not very strongly because van der Waals forces are not very strong. If I draw the lattice structure solid C60, is something like this. This is one carbon 60 molecule, carbon 60 molecule, carbon 60 molecule. Likewise, you know how you draw metallic structure? This is not the metallic structure, but similar diagram. Only difference is in metallic structure, there are electrons in between. But in buckyballs, you don't have that sort of electrons in between molecules. So this can be referred to as carbon 60 lattice structure. Bonds are arranged the way how I have given the answer. And then C60, next question. C60 sublimes or turn directly from solid to gas at about 800 Kelvin. Diamond also sublime, but only about 3,800 Kelvin. Explain why C60 and diamond sublime at such different temperatures. It's because diamond has only covalent bonds. Buckyballs have van der Waals forces and covalent bonds also. First, I'll talk about covalent diamonds. There are only strong covalent bonds between atoms in diamond. A lot of heat energy is needed to break these bonds to sublime. However, there are weak van der Waals forces. There are weak van der Waals forces between buckyballs. Between buckyballs. However, there are weak van der Waals forces between buckyballs. Buckyballs means C60. They can be broken down easily at lower temperatures. Hence, they sublime at lower temperatures. Four marks are there. We'll move on to the next one. We'll go to the next one. C60 forms hydrocarbons with similar chemical properties to those of alkenes. One such hydrocarbon is C60H18. Okay. State what is meant by the term hydrocarbons. They consist of only carbon and hydrogen. They consist of only carbon and hydrogen. Or as you can say, they are compounds. They are substances. They are substances that consist of only carbon and hydrogen. Okay. Our next question. Describe a test to indicate the presence of double bonds between carbon atoms in C60H18. If there are double bonds between carbon atoms, the test is add bromine water. It's a standard test. The result is red-brown color of bromine disappears. Red-brown color of bromine disappears immediately. Red-brown color of bromine disappears immediately. Yeah. When you write, if you write the bromine using symbol, don't write just Br, write Br2. Br2. And the next question is something we have to think about. If you don't think, then you will never get the answer. Question says, a 0.144 grams of C60 was placed in a 100 centimeter cube container of hydrogen gas at 20 degrees Celsius and pressure is given. The container was heated to make the C60 and hydrogen gas react. Let's see. The reaction occurred as shown in the equation. C6 react with hydrogen. We don't know how many hydrogen. After the addition, the container was allowed to cool to 20 degrees Celsius. The pressure decreased to some value. All of the C60 had reacted. Name the type of reaction that occurs. If the compound has double bonds, the type of reaction happening is addition. Addition. If you want to be very precise, we can call it electrophilic addition. Electrophilic addition, that's a typical reaction type of alkenes. Next one, calculate the amount in moles of C60 that reacted. Because everyone is used to the formula, I also will do the same thing. We want to find the moles. Moles is equal to mass over molar mass. Mass is given. Mass is 0.144. 0.144. Molar mass means 12 into 60, because there are 60 carbon atoms. Plus, there's one more thing. Carbon 60 and yeah, only carbon 60. That's it. Carbon 60 means 840 grams per mole. So mole is equal to 0.144 over 840. Answer you get and write over there. when you divide 0.144 grams by the molar mass of fluorine, which is 720, this is gram per mole, I get here 2 into 10 to the power negative 4 moles. These moles are reacted with what? With hydrogen. Question wants you to find out the amount in moles of hydrogen gas that reacted with C60. Question tells that this fluorine was added into hydrogen. Container volume is given, temperature is given, pressure is given. If you know the volume, temperature, and pressure, we can find out the moles of hydrogen gas. Once the reaction is over, again the same, similar value, not similar values, the same parameters have been given. Volume is there, temperature is there, pressure is there. Now there's a different value. Why there's a different value? Earlier there were hydrogen. Some of the hydrogen react with C60. And after some time we have a different amount of hydrogen gas. If we can find out the moles of hydrogen earlier and moles of hydrogen finally, by the difference of the moles, we can find out the hydrogen moles reacted. I'll write it like this here. Hydrogen reacted. H2 reacted is equal to H2 initial minus H2 final. When you want to find out the moles of a gas, by PV is equal to nRT, N is equal to PV over RT. So for the initial hydrogen moles, we'll write PV RT. For the final also, we write PV over RT. So I write initial hydrogen, PV over RT initial minus PV over RT final. Here volume is the same, RT, everything is same, only the difference is P, pressure. So we can say P initial minus P final into P over RT. This is the hydrogen reacted, 0.32 moles. Okay. Now we can write pressure initial. What is the initial pressure? Initial pressure is 10 to the power 5 Pascal. Initial pressure is 10 to the power 5 Pascal. Minus final pressure is 2.21 in 10 to the power 4. 2.21 into 10 to the power 4. Into volume is given as, what's volume? 100 centimeter cube. Volume is 100 centimeter cube. But 100 centimeter cube, I had to write as 10 into 100 into 10 to the power 6, because I would have the unit in meter cube. I'll rewrite it. Volume is equal to 100 centimeter cube into 10 to the power negative 6 volume. R is 8.31 into temperature is 20, 293. You will get this value in molar. You can get the answer for this. The simplification will give you 3.2 into 10 power negative 3. This is the amount of hydrogen gas in moles. Now see, C60 is this many moles. Hydrogen moles is this much. We had to use these answers 2 and 3 to deduce a molecular formula of hydrogen. We'll write C60 H2 moles. We have 2 into 10 to the power negative 4 moles. This many moles of C60 have reacted with 3.2 into 10 to the power negative 3 moles of H2. We can find out what the lesser one. Smaller one is this. So to find the mole ratio, we divide both by 2 into 10 to the power negative 4. That gives me 1 from here. When you divide 3.2 into 10 to the power negative 3 by 2 into 10 to the power negative 4, you get when you divide C60 moles and H2 moles by the smallest number of moles, I get C60. This is 1. H2, 16. Now, when you say H2 is 16, H is 32. So molecular formula of the compound is only carbon 61 means there are carbon 60 and hydrogen there are 32. This is a formula of the newly formed carbon, hydrocarbon. D point. Silicon shows the same kind of bonding and structure as diamond. State the type of bonding and structure shown by silicon. You can see silicon has a giant covalent lattice. Silicon has a giant covalent lattice structure where all the silicon atoms are bonded together through strong covalent bonds. Where each silicon atom binds to 4 other silicon atoms in tetrahedral manner. When silicon reacts with magnesium, magnesium silicide is formed. So Mg2 silicon is thought to contain silicon plus 4 ion. Yeah. State the full electronic configuration of silicon -4. Silicon has 14 electrons. 14 electrons. But when silicon changes to silicon 4-, it gives 18 electrons. So electronic configuration must be written for 18 electrons. 1s2 is there already. 2s2, 2p6, 3s2, 3p6. Solid Mg twice Si react with dilute hydrochloric acid to form gaseous SiH4 and magnesium chloride solution. Balance equation is Mg twice silicon plus HCl given SiH4 plus magnesium chloride. MgSi is solid, HCl is aqueous, silicon hydride is gaseous, magnesium chloride is aqueous. Because we have magnesium 2, I write twice MgCl2. And chlorine is 4 here, so you write 4 over here. It's balanced. Next one, predict the shape of the SiH4 silicon hydride molecule. Silicon has outermost 4 electrons. Silicon has 4 outer electrons. When silicon makes 4 bonds with 4 hydrogen, 1 electron goes to each bond. So the 4 outer electrons will be used up to make 4 bonds. There are no lone pairs of electrons. There are 4 bonds, then the shape is tetrahedral. Next question says, SiH4, all right, SiH4 reacts spontaneously with oxygen to produce white solid. What is the white solid? Silicon dioxide. And a colorless liquid that turns anhydrous copper-2 sulfate blue. If a liquid changes anhydrous copper-2 sulfate, which is white, to blue, definitely that liquid should be water. Water can make white copper sulfate blue. Silicon hydride, because we have 4 hydrogen, I write 2 over here and 2 oxygen to balance the equation. That's the end of the question number 2 in 2018, February, March 22 paper. I think there are no big difficulties in this question. So let's stop the work over here.